Okay. So, welcome everyone. I'm Deborah Isaac. I'm the founder of Houdini School, and welcome back to Solver Madness. So, I'm going to hand it over to you, Andrew.
Yeah. Thanks for joining us. A lot of really exciting stuff to dig into today. In fact, we're gonna try to cover a lot of ground. So I feel like we got a lot of the basics in the bag on the first session, really setting the groundwork for what we're going to dig into now, which is actually building this effect from start to finish. So should I go ahead and share screen?
Yep.
Yeah, let's do this. Okay, how are we looking here?
Great.
All right. So as you probably saw in the teaser, this is the finished effect that we're going to build. And a couple notes. The student file that I gave out last time actually has a setup to do this. I would disregard that because I've done a lot of work with it to try to streamline it for this course in a way that makes more sense and optimized a few things. So you can actually disregard that file in general because this one, the student file that you're getting today, has everything you need, including the stuff we did with the growth solver, along with a couple of additional explainers, which we can maybe dig into if there's time. So without further ado, we'll leave these open. We might come back to reference them. All right. So this is the overall flow of the effect we're going to do. And as you can see, there's a lot of ground to cover. And the way I'm going to go about it is just so it's not confusing to folks, I'm going to be switching between a kind of blank canvas area here that has containers for the major simulation processes that I'll copy and paste and build step by step. So when you see me kind of doing these quick mark jumps, that's what I'm doing. I'll be going back to our master setup to grab things and bring them over. The other thing is to keep in mind is I do have a cache demo PDG network in here that I'll be adding to. And this is really for demonstration purposes. You should have in your file the actual caches that are being done at the object level here, object level top net that has the entire thing. And theoretically, once you set your cache variable path to something that makes sense for your local path, you should just be able to run this final node here called cook me, and it'll give you all the caches you need. And that's going to be slow. So it's up to you whether you want to do it during the class or after. But that's all there and ready to go. Excuse me. Also, bear with me a little bit if I cough because I am recovering from COVID. So I will try not to cough too loud in the microphone. Let's see. Let me look up notes and see where to start. Control panel. We talked a little bit about global control panels in the last chapter, and we'll get into that a little bit more in this one as well. I haven't really built much other than the frame range that we're going to be working from, and I also have a couple of the file cache reads set up and gathered here, including a technique for setting the version of your caches, which we can go over later. And it's just handy, as we talked about earlier, just to have them gathered in one place. All right, so let's start with Pyro. If you'll remember in our flow chart, everything, all the simulations are going to be advected with Pyro. So that's the first thing we want to put together is a Pyro sim that we can source downstream into our simulations for advection. So to begin with, we're bringing in our source points. And actually, before I do anything, I also need our control panel and global bounds. Let's talk about that real quickly. So control panel, which we already discussed. Global bounds is really just a box. That's what it is. It's a box. And we want to set the domain for all of our simulations. So begin by setting a camera angle, even if it's just a temporary angle for the simulation that you're working with. It's important at this stage to work from a certain viewport, viewpoint. And then you can set the bounds to that, even if that changes later on. As you can see, that's what I have right here. It's matching my view. And what that means then is every time we add a new solver or simulation, we can reference that. And starting with the pyro, which we'll go over next, this is all I've done is I've taken the dimensions, copy parameter, and gone into the size, the bounds of the pyro sim and paste relative reference, and then limit maximum size. And this is a very important optimization that's used throughout all the simulations we're going to be doing. All right, so source points that we're familiar with from the last setup. And really, these just have one attribute on them. Well, two. They have p-scale and they have velocities. Velocity in the general direction of growth and a p-scale. Next, dropping down a pyro source. And this is all default. The only addition is that I've added a velocity attribute so that we can, so if you dropped in a pyro source, I think by default, if you initialize smoke, you're going to get density and temperature. Add a new attribute and call it velocity, you're good to go. That'll get the point attributes we need for the next node, which is volume rasterized attributes. Volume rasterized attributes will take the attributes we feed it, density, temperature, velocity in this case, and put those into voxels so that we can use them in volume simulations. So that's the output of that. Next, pyro solver. I'm actually going to drop down a pyro solver. I might as well. And you know what? In this case, I might not, just because we already have settings and there's not a whole lot we're doing with it. It's fairly straightforward what we're doing with the pyro solver. Starting with the sourcing. And really the only thing is, well, we're sourcing density, temperature, and velocity. It's just the attributes we've rasterized. And taking velocity and changing the source scale to -20. Because as you remember, the growth solver has vectors in the direction of their travel of the growth, and we want it to go in the opposite direction. So bear with me a minute here. It looks like my drives are trying to spin up. In the last session, also, somebody asked a question about using buoyancy. And I think I might have misheard or misunderstood the question. So I wanted to come back to that briefly. And I think the question they were asking is why not use buoyancy in the pyro sim to get upward motion? And the answer is you totally can. In fact, we are. But we also want to get the primary velocities from the growth solve because we get these great shapes. And we get much more of a sinuous shaping in the direction of the actual geometry source. Then after that, we can add additional shaping to it. So in the shape here, we are adding some buoyancy, 0.5, give it some upward motion, and cheating a little bit more of that upward motion with wind. And then these are fairly standard if you've ever used pyro disturbance and turbulence to add some detail. And a lot of these settings are going to be very arbitrary and depending on what kind of simulation you're working with. So it's totally dependent on what you're doing. Beyond that, uh, there's not a whole lot else. The voxel size is nothing crazy. Again, this is really all we need is velocity from this. And that's that. We're ready to go to the next solver, unless there's any questions.
Any questions? I think we're good.
Okay. All right. Bear with me one moment. All right. So the next thing we need is our flip simulation. This is kind of fun. This is a different approach to doing flip than usual, where we're going to treat it more like a particle system. And we're going to set an age attribute and have them die after a certain point. And the reason is, if we go back to our render here, what we want to do, the effect we're trying to achieve, is we want to have a solid sourcing as our geometry sort of liquefies. And then we want that to sort of dissipate around here and start spawning bubbles at the end of a lifespan on the flip that we'll set. So we'll have these bubbles and smaller little foamy particles. And that's the next step of the simulation that we're going to set. So, make sense?
Yep.
All right. Let me go ahead and just disable everything and can go through it step by step. So we'll start by just turning these off. All right. So once again, our growth score, excuse me, growth source points. And this time we're doing a VDB from particles to create a distance VDB, which is what the flip dop source node wants to have. That'll turn it into a VDB source that the flip solver can actually read. Now, you could probably do this with the SOP level flip solver, the newer one. This particular effect is, to me, probably simpler to do it in a DOPNet from scratch, which is how it's built. So we have the source for our flip particles coming in on this first input. And on the second input, we're going to bring in velocity. And the reason we want to split that is because you don't actually have to use as much resolution on your VDB volume for velocity. So you'll see here, the flip sourcing for the particles is 0.025, and for velocity, it's set to 0.05. Along with that, it seemed to help a little bit to add a little bit of curl noise. So if we look here, here's our, not a whole lot, just a little bit of curl noise to the incoming velocity. And then in order to bring in that velocity, let me just run through this real quick. Video from particles, you have to set a minimum radius. It's going to capture all the points. 5. And then add a point attribute. You'll see you can find the point velocities right here. Select that and make sure the vector type is set to displacement velocity acceleration. V is how velocities are tagged in Houdini for points. And since this is a volume, we want that to be named vel. So that's already set up. And now we can dive into the DOPNet. Let me back to 0. All right. A couple things here. First of all, this flip source is creating particles for us, which we're sourcing into the simulation. And that's important. In the flip solver itself, if I drop one down, I'm sorry, in the flip object, you'll see it will default to surface SOP. And what you're going to want to source in is particle field and delete this SOP path. This creates some particles to start with default, and that's not needed. So you can get rid of that. I've already done that here in the flip object. So we should be ready to go. And I've set a particle separation as well. Next, we're sourcing in the velocity and volume source. In fact, what I'm going to do is disable these and go over their settings because that's kind of important. First of all, let's source velocity. We know it's coming into the second input. And what we want is a vector, and we're sourcing vel and targeting vel and adding that. And we can wire that into the volume velocity. Make sure I didn't have any. Might as well turn that on. And make sure we want to source particles. I don't think in this case it matters. We're just using velocities. And then for the actual particle sourcing, add in another volume source. And this will be the first context geometry. And you can initialize source flip. That'll give us the surface. And then in this tab, this is where it's important to set a few things. Life expectancy and life variance. In our case, I believe we're using, let's see, life expectancy of 1 and a variance of 0.025, which means that the particles we create in flip will have a lifespan of 1 plus or minus a quarter of a second. So 1 second plus or minus a quarter of a second. And we don't need this. Now, in order for that to work and to take effect, I'm going to go ahead and go back to the ones I've already created. In order for that to work, you have to go to the flip solver here and select a few things in these toggles. The main ones being age particles, which means it does create an age attribute per point, and reap particles, which means they will be killed when they go beyond their lifespan. Also, we'll need an ID attribute, which is not on by default. And like we covered earlier, it's important for us to also set the limits. So I believe it's already by default, it's set, but that you're going to want to have that linked again to your global. Because then if you have a new shot and you've changed your camera angle, you can change your domain and everything updates. Paste relative reference. All good?
Yes, we did have a little conversation here about why you don't need to specify the SOP path. And it's because you're sourcing with the volume instead as continuous emission versus that default SOP that you deleted earlier.
You are correct. That is totally correct. We're sourcing particles continuously from this flip dop source.
Awesome.
I believe that's everything we need, and we might as well run it for a few frames and see what we get. Another thing that's maybe a little eccentric in this setup is that I'm advecting the flip particles with that pyrosim. And the reason is, it just gives us a little more shaping and these sort of sinuous um, lines, kind of shaping that follows the contours of the source geometry in a very cool way. So you can see also this is not a very high res flip sim either. It doesn't need to be. And unlike a lot of flip simulations that are very dependent on the scale of your scene, and you have to set very specific particle separations, this is entirely arbitrary. It's really more of a stylized effect. So in our flip sim here, we're advecting both the force and the velocity of those flip particles by a small amount. So a little bit more than a third on the velocity, and looks like, yeah, 0.12. I mean, on the force, and 0.12 on the velocity. So actually, those are not linking. Let me make sure that we're grabbing them. So yeah. And the effect is fairly subtle, but it's there. Then pop force is giving us some upward, a little more upward velocity and some noise. And that gives us our flip simulation. And let me actually, this is already cached, so let's go ahead and look at this. In this situation, also we do need the flip points. We're looking at the cache now. I'm gonna turn this off. So as you can see, we get some nice shaping around the edges of our martini glass, and that's going to blend in nicely. And you can also see the effects of our growth solve and how much that's adding to the simulation. Also, while we're here, let's just add a color ramp. And we'll look at age. So as you can see here, that's our age attribute. And what's red right now is really what we want to be looking at in terms of creating additional sourcing into downstream simulations. So I'm actually I'm meshing this as well for use later on. It's all going to get combined later on, and you can totally use the particle. What is it? Fluid surface, particle fluid surface SOP to mesh these points. I've generally had better luck meshing things manually with VDB, and we'll step through that in a minute. But first, I want to go over sourcing for other simulations. So as we talked about earlier, we want to just get points at the very end of the lifespan of this flip simulation to create bubbles and foam at that stage, and a smooth transition from our flip simulation to particle simulation. And the way we're doing that is it's a two-stage process. First of all, culling a percentage of the points. It's, as you can see, it's pretty dense. Flip tends to, depending on your particle separation, create a lot of points. And we only need a subset of those to spawn new particles. So I believe Houdini has a SOP now that you can call points easily, but I'm used to doing it old school where you just use a vex expression. And since you can do this inside of all kinds of vex expressions, it's handy. And all I'm doing here is that I'm saying I'm getting a random number on all these points based on their ID, which is why we needed also that flip ID attribute activated. And then it's saying that if it's less than this threshold slider, then delete that point number. So essentially, this just becomes a percentage slider. So if I slide this down, and then of just calling out the points we don't need. 0.98, I believe, is what I had. Yeah. Next, since we've called a lot of the points we don't need, now we just need the ones at the age that we want to spawn new particles. And this is another expression that's just saying if the age is less than this slider, then remove that point. And that gives us any of the points that are above an age of 0.785. And those will then become the, put a null here. These will be flip trail source. I'm calling it trail source, and those are the more foamy, smaller particles. Excuse me. And then we're also creating a sourcing for the bubbles, which are trying to, here we go, which are these larger ones here. And that follows a similar process where we're calling some points. And then in this case, removing a different age range. We want these bubbles to source over a wider age range, age range of the flip sim.